Okay, I'm going to give you an overview of complex numbers in 10 minutes, if possible. So, complex number C. C equals a real number x plus a real number y times the imaginary number, where the imaginary number is defined as the square root of -1. And you may have seen this before plotted on an axis, like so. So the real part of C equals x, the imaginary part of C equals y. And so if you want to plot a number C, what you do is you go over x up y. So let's just say x is 4 and y is 4. Then you get a point on the complex plane, point C on the complex plane. That was probably just about everything you learned in algebra about complex numbers in 4 seconds. So the next most important things to know about complex numbers is I'm just going to throw a bunch of equations at you that are identities and things that are important for you to keep in mind moving forward. So there's something called Euler's equation. Euler's equation, and that is e to the I theta equals cosine theta plus I sine theta. If you plug in theta equals pi, you get Euler's identity, which is e to the I pi plus 1 equals 0. And there's a proof of this on Khan Academy, which I encourage you to check out. Using Euler's equation, what we can do is we can get identities for cosine and sine. Isolating them, you would get cosine of theta equals e to the I theta plus e to the negative I theta over 2, and sine of theta equals e to the I theta minus e to the negative I theta over 2I. These are identities for sine and cosine coming from Euler's identity. And these are super useful. Keep these in mind if you go into calculus and you're trying to solve a tough integral that has sines and cosines in it. You can use these identities a lot of times to help you. It's much easier to manipulate exponentials than it is sines and cosines, is all I'm trying to say. So if you keep those in mind, that'll be helpful. But another thing that's useful is hyperbolic sine and hyperbolic cosine. If you're in Calc 2 or if you're going into Calc 2, you will see these or have seen these. Hyperbolic cosine, cosh, is simply defined as cosine of I theta. And from this, you find that cosine of I theta is equal to e to the theta plus e to the negative theta over 2. Sinh is defined a little less intuitively. It's defined as negative I sine I theta. But the negative and the imaginary number in there are just due to the fact that you have an imaginary number here, and that this minus sign makes sinh look less similar to this identity for sine than if you had multiplied it by negative I. Anyhow, what that ends up being equal to is e to the I, just e to the theta minus e to the negative theta over 2. Right, and that's where those come from. If you were wondering why sinh and cosh were so weird and how they were related to cosines and sines in the first place, well, this is why and this is how. So hopefully that's at least a little bit insightful. Now, given that, we have a few more things to cover in, we still have 5 minutes. So some of the most important things to touch on are the relationship between polar coordinates and Cartesian coordinates. So you have complex number C equals x plus yi, and you can convert this to a magnitude and an angle. C equals magnitude of C times angle C, or another way of saying that is magnitude of C e to the I angle of C. Whoops. Angle of C. And this is standard notation in electrical engineering. Whenever you start dealing with phasors, which is a rotating angle, but I'm not going to get into that in this video. I will get to that at some point in the future. So what you have to do is you have to figure out how are these two related? How are these two related? And so the absolute value function, you've probably done that a million times. So you have, whoops, magnitude of C is very simply x squared plus y squared, the square root of that. And the angle C comes from what's equal to is angle C is equal to e to the I. Oh, it's not equal to e to the I. What it's equal to. I did this wrong. Up here, it's not magnitude angle. It's true that this is okay. This is angle C, but this wasn't angle C. This is supposed to be an actual angular measure. This is related to something slightly different. This phase is related to the exponential in a more complicated way that I'm not going to get into. But anyhow, so we have this angle. Turns out that it's equal to e to the I inverse tangent y over x. And that just comes from the fact that on the complex plane, if you go over x and up y, right, x, y, you have a kind of a triangle corresponding to that. Well, tangent is opposite over adjacent, where opposite is equal to y, adjacent is equal to x. So you have we'll call this theta, tan theta equals y over x. Therefore, inverse tangent y over x equals theta. So that's where this comes from. But that's really what I wanted to get to in this video, is that you can have a relationship between Cartesian coordinates and magnitude angle coordinates, in the sense that C equals x plus y, I equals square root of x squared plus y squared e to the I inverse tangent y over x. One last thing I'm going to touch on: complex conjugates. Standard notation, C star. This is, you take this I, you take any I you see, and you turn it into a negative I. So the complex conjugate of C, denoted by this star, is equal to x minus yi. The complex, so that is also equal to square root of x squared plus y squared e to the negative I inverse tangent y over x. The negative sign comes in. So the complex conjugate, you just, every I you see, you turn it into a negative I. So this plus goes to a minus, this plus goes to a minus. And that's everything that you need to know about complex numbers in 10 minutes. One thing that's also important to keep in mind, though, is whenever you have a complex conjugate times the complex number itself, what you ultimately end up getting is just the real component squared.